Welcome everyone. So we are discussing about the X-ray and X-ray spectrum. In last class, we first discussed about the how experimentally X-ray was discovered by the Rontgen, and then we discussed the properties like wavelength, frequencies, these properties, soft X-ray, hard X-ray, these things. And after that, we discussed the X-ray spectrum. There are two types of spectrum: continuous X-ray spectrum and the uh, characteristic X-ray spectrum, and two X-ray spectrum are actually superimposed, and that is the total X-ray spectrum. We have already shown that, and also we have discussed the reason behind the spectrum. So in this class we will discuss about the Moseless experiment basically, and we will figure out how Bohr's theory can explain the Moseless result, because Bohr's theory is totally hypothetical, and because there was no theoretical background behind the ad hoc postulates of Bohr's. We are already now familiar with these things. Now we have totally discussed in this course throughout. But one of the most beautiful example we can say that Bohr's theory can be applicable to explain the Moseless results, Moseless observation. So that we'll discuss today. But let me start with the X-ray spectrum again, because in last class we discussed, but in this class we'll elaborate this little bit. Not elaborate, we can say we'll recap this little bit, and then we'll go to the Moseless result, and then theoretically this course will be finished. And after that, after few classes, 1 or 2 classes, we will discuss about some numerical examples, numerical problems, these things. Okay, so our today's class is about X-ray. Okay, as I mentioned yesterday, not in the last class, that if you look at the spectrum, how it looked like, if we see the X-ray spectrum, then here is the relative intensity, in y axis, and in z axis there is wavelength of X-ray in nanometer. If you plot it, it is 30, it is 90. This is for molybdenum atom, molybdenum metal. So now if you look at the nature of this X-ray, then you can see this is actually like, this is a part, we can say this is continuous part, and there are two characteristic peaks. One is obtained around 60 nanometer like this, and another one like this. There are two characteristic peaks, and if you superimpose these two figures, these two spectrum, then we can visualize the spectrum like this. This is the spectrum, and this is called K alpha peak, this is K beta peak, this is around, we can say around, it's around 65, 63, 65, and this peak around 70 nanometer. Okay, and this value is actually the lambda mean. So this is our total X-ray spectrum. Now we can see here there are two peaks, characteristic peaks, K alpha and K beta, and other spectrum is totally continuous spectrum. So what was the reason behind this kind of spectrum? So now there are actually, let me write it. So if you now classify, then one is continuous X-ray spectrum, and another one is I will just recapitulate the things, because in last class I have already explained these results, why this is happening. So if you recall the experimental setup, what was the experimental setup? This is kind of cathode tube. Okay, so this is negatively charged electrode, this is positively charged electrode, and in this tube the electrons, which is actually the cathode ray is traveling from one electrode to another electrode in a high velocity. This was our cathode ray experimental setup of cathode ray. Now what Ranjan did, he put there a metal. This is a metal in the path of the cathode ray. Then when the cathode ray bombards here, let me change the color first. When the cathode ray bombards here, then X-ray basically emits. Okay, this was our experimental setup. So this spectrum is actually characteristic spectrum for any metal. Here this is for molybdenum metal, this metal is molybdenum. If instead of molybdenum you put other metal, then the spectrum will look different. The peaks will be in other position for other wavelength, that will be the thing, but overall picture will be remain more or less fixed. Okay, so this is our X-ray spectrum and this is experimental setup, we know. Now continuous spectrum, what is the reason behind this continuous spectrum? Okay, so let's say we are now, if you look at this metal, we know every element in the world, in the universe, every element is actually made by infinite number of atoms. Okay, and atom is actually very tiny particle. We have already discussed these things, right? So now if you look at the just atom which is just around, at the boundary of that metal, that atom will be collided by that cathode ray, that electron. Cathode ray is actually the flow of electrons. So when, let's say this is metal and the electron is flowing, cathode ray is flowing, and it actually bombarded here. Now what will happen? This actually get collide with the atoms of the metal surface, right? There are lots of atoms. So let's say we are taking one atom in the metal surface with which the electron is colliding. Okay, now take a atom. We are considering the Bohr's model, Bohr's atomic model, because we know atomic structure. So let's say this is our atom at the surface of the metal, and electron is coming and it will get hit here. Okay, so now let's say the velocity, the primary velocity of electron was k naught, and electrons collided with that atom. You have to keep in mind that there are lots of electrons in the atom as well. So when electron collides with the atom, what will happen? Such amount of energy will be decreased, will be lost by the electron, and the energy will be k naught minus delta k, we are assuming. So delta k amount of energy is actually decreased. So this amount of energy, what is the fate of this amount of energy? Where does it go, right? One possibility is there, the atom absorb this energy, but that is very less probable, and the amount of that, actually if you consider, the probability is very negligible, because atom is much more heavier than electron, right? So that's why we can say atom is not absorbing this amount of energy. This amount of energy, this delta k amount of energy, actually converted into the wave, into the wave, or we can say into the X-ray. It can be other thing, not only the X-ray, but this can be that depends upon the del k, the energy, right? Because we know E equals to h nu, so each energy corresponds to some frequency, right? Frequency photon. So if the energy is sufficient, then sufficient to produce a photon of X-ray, then this amount of energy will be converted into X-ray. So this is the whole thing. So this del k amount of energy actually is converting to the X-ray photon. So, and we know what will be the frequency of that photon? H nu should be equals to the del k, or we can say nu will be del k by h, and we know nu c equals to nu lambda. So if you put it here, then we can write it c by lambda del k by h. So from here we can write lambda equal to h c by del k. So this will be the wavelength of the emitted photon of X-ray. Okay. So now if del k increases, essentially if the energy increases, frequency will also be increased, and obviously lambda, or the wavelength, will be decreased. We can see it from here as well. Now let's say there is not only one collision, right? This electron, this emitted electron with the energy k naught minus delta k, it will again collide because there are lots of atom in the surface of metal, then there will be successive collision will be there. So we can say and each time the del k will not be the same. Obviously there are various types of del k, so there will be a various type of lambda. So we can say that there will be each lambda will be actually observed. So that's why the spectrum will be continuous. Continuous means there will be each lambda. Obviously the intensity would not be the same, the intensity of photon for each lambda will not be the same. We can see it from here as well. This is actually intensity, the intensity is less, then it's increasing, right, increasing, then it gets peak. This peaks, reason behind these peaks are different, but still the intensity is not same. That will happen all obviously because del k is the change in energy which actually reason behind the releasing a photon of X-ray. So that is depends on the del k, and del k is not fixed for the each collision. So there are several collision, several types of del k, so there will be different of lambda. Okay, so this is the reason. Also you have to keep in mind that only one electron is not colliding with the metal surface, there are lots of electron colliding. So there will be infinite number of, we can say innumerable number of del k is there. So that's why it will have all of lambda will be. So that's why this is continuous spectra, and for each lambda there will be different types of intensity. So that's why we can see here from the peak, what is the, this is the peak, the intensity actually variable, it varies, it's not constant. So this is the reason. But one more thing, it's important. Let's say for the first collision, during the first collision, if total amount of energy is converted into the X-ray photon, then what will happen? The electron will be stopped. Okay, because it will have no kinetic energy, k will be 0. So in that case, del k is actually k naught. Okay, then only this will be 0. So in that case, the lambda will be minimum, because del k should be less equals to k naught. It's the fact. K naught is the kinetic energy of the electron before the collision. So del k, it can be less than or equals to k naught. So del k, the maximum value of del k is k naught. So the minimum value of lambda should be hc by k naught. So this is our lambda mean. Okay, so that's why this is lambda mean. From here we can find out the k naught. Actually this depends upon, this depends on the k naught. The lambda mean equals to hc by k naught. It depends up to us. So this is our continuous spectra. Okay, so now coming into that, what is the reason behind these two characteristic peaks? This is very important, k alpha and k beta, because from continuous spectrum we will get no information. This is kind of same for each and every metal. So this does not depend upon the metal, but these two peaks, k alpha and k beta, is essentially depends on the types of metal, which metal you are taking for the experiment. For molybdenum, we can see there are k alpha and k beta. Okay, there is one mistake actually. This is k alpha and this is k beta. Let me correct it. Okay, so this depends upon the metal characteristic. That's why it's called characteristic spectrum. Now, what is the reason behind this? So again, if you look at the atomic structure, let me, okay. Okay, so let me, so this is our atom. So now when the electron is colliding with any atom, what I mentioned, that there are also several atoms in the several electrons in the atom, that electrons are actually circulating around the nucleus. So while passing through the atom, the electron of cathode ray will actually can collide with that electrons as well, and due to that collision, one electron can be kicked out, one or more than one electron can be kicked out from the atom. Let's say for visualizing, one electron, this electron, the red color electron is electron of cathode ray, right? Let us assuming that it comes and it goes, but during this collision, this electron also emitted, kicked out, the electron of cathode ray kicked out one electron from the k orbit of atom. This is k, l, m and such on. So what will happen in that case? There will be a vacant place in k orbit. So after this collision, what will happen? Here one vacuum will be created. Okay, this is the vacuum. So then to fill up this vacuum position, electrons from higher orbit, can be from here, higher orbit will jump to the k orbit to fill up that vacuum position. And we know from the Bohr's atomic model, during this transition from higher energy level to lower energy level, the energy will be released. Okay, and the formula is that daily should be equals to the h nu. That daily is the energy gap between those energy levels. Okay, from the excited level to the ground level, and corresponding wavelength, the photon of the corresponding wavelength will be released. That's the case. That's the reason behind the characteristic X-ray spectrum. So you can argue that there will be different types of orbits. It can be K, L, M, N, O, lots of orbits are there. So electron can be kicked out from any orbit, right? It can be kicked out from P, and it can be then electrons from higher orbit that can then from, if electrons kicked out from the p orbit, then you can understand that from higher orbit also the electrons can be come into the p orbit to fill up that position. For that also there will be some release of energy, that will also give some photon, but that energy, that photon will not be corresponding to the X-ray photon. Actually, you know that from our discussion from Bohr's model, we know the atomic levels. This is our n equals to 1, n equals to 2, then these gaps are decreasing, right, like this, getting closer, this goes on. So you can see the energy gap between two successive level decreases if n is increasing. So now X-ray means, if you look at the spectrum, if it is our visible range, then X-ray, after visible range there is, here is our ultraviolet, here is IR, after ultraviolet there is X-ray. So we can see the lambda of X-ray is very less, this so energy will be higher. So that means the energy gaps would be higher. That's why the transition energy which correspond to the photon of the X-ray, that will be reason for this characteristic X-ray spectrum. Not each and every transition, there may be other transition, and there may be other photons which can be photon of UV ray, which can be photon of visible region, that also can be, but we are interested in the X-ray photon. So that will occur when the electron of the k orbit is kicked out, and to fill up that position, if one electron comes from L or M orbit, then that energy gap, actually corresponding to the photon of the X-ray. Or if one electron is kicked out from the L orbit, and to fill up that gap, if one electron is coming out from the N orbit or M orbit, then that energy gap also corresponding to the photon of X-ray. So there are 4 essential transitions which actually corresponding to the emission of the X-ray photon. So what are those? Let's say if we draw K, L, M, N, K, L, M, N. So if there is a vacuum in k orbit and one electron comes from L or to M, then this energy gap actually corresponds to the X-ray. So this is 1 and this is 2. And if there is a vacuum in the L orbit, then electron can comes from M and N. So these 4 transitions are actually governs for the emission of X-ray photon. Okay, so there are 4 peaks will be there. This transition, the peaks due to this transition actually K alpha, this is K beta, L alpha, L beta. So these are the 4 characteristics peak. We can see here K alpha and K beta only, but there will be more 2 peaks. The intensity of those peaks are very less. That's why that emerge with the continuous spectrum, we can say. So this is our 2 types of X-ray spectrum. So in this part, let me stop here. In the next part, we will carry forward from this part, these characteristic spectrum, X-ray spectrum, and we will study the Moseley's law, Moseley's experiment. So thank you.